When dealing with the regeneration of reinforced concrete built heritage, the structural assessment is a pivotal activity. The performance-based approach provides the proper conceptual framework to carry out this assessment within a sustainability perspective. The approach focuses on the ability of a structure to fulfill performance requirements for the designed or remaining service life at required probability level. The structural assessment calls mainly to combine structural, such as safety, serviceability, durability, robustness, and cultural heritage requirements, such as minimal intervention, reversibility, compatibility. The difficulty lies in balancing technical, cultural, economic, and social factors, given that all these factors are characterized by uncertainties. The assumption of responsibility by the professionals involved in safety assessment, design, and execution of intervention is a key issue. In essence, for reinforced concrete built heritage, the goal is to guarantee adequate structural safety level without altering the fabric tangible values. This is achieved by pursuing a dual goal. On one hand, mobilizing residual load-bearing capacity to minimize or avoid intervention. On the other, by mobilizing awareness and recognition of cultural heritage tangible and intangible values. By restricting ourselves to the structural domain, accurate analyses are needed to mobilize the residual structural capacity by increasing the level of approximation. This entails more time and higher costs for the analysis. The structural assessment can be divided into three phases: the knowledge phase, the performance evaluation phase, and the safety verification and interventions design phase. A reliable knowledge of the current state, in terms of design, materials, execution, degradation, is the key starting point of the assessment. It consists of historical critical analysis, geometric and structural survey, mechanical characterization of materials. Specific aspects to be considered in this phase for reinforced concrete modern heritage are analogies, patents, construction systems, survey techniques, diagnostic testing, whether they are destructive and non-destructive, and structural health assessment. To give you an example, the limitation of the invasiveness of investigations for materials characterization in favor of the use of thorough historical research, accurate surveying operation, and non-destructive diagnostic technique is to be considered. The performance evaluation phase hinges on the definition of limit states, on the definition of the actions, whether they are permanent, variable, accidental, on the type of analysis, and on the true life performance. Specific aspects to be considered in this phase for reinforced concrete modern heritage are service life, structural codes at the time of construction, seismic action, and partial factor, together with degradation models, ductility assessment, durability, and reliability index. For instance, the service life is conventionally defined as the number of years in which the structure, provided it is subject to necessary maintenance, is expected to maintain specific performance levels. Design service life refers to new structure, and remaining service life to existing ones. For the latter, the service life shall be calibrated to find a proper trade-off between life extension and demand assumption. The safety verification phase involves the choice of the method of verification, the level of approximation, the type of verification, either strength, durability, robustness, sustainability. Specific aspects to be considered in this phase are risk-informed methods, reliability-based methods, semi-probabilistic methods, deemed to satisfy approach, assessment by avoidance approach, and assessment assisted by monitoring and testing. For instance, when using risk-informed assessment method, the reliability of an existing structure with significant failure consequences due to loss of cultural heritage value shall be verified by comparing the expected risk to the corresponding target risk level. Or, for shear resistance calculation, highest level of approximation shall be adopted in considering cases with and without shear reinforcement. As far as the strategies for consolidation and reinforcement is concerned, the enhancement of the capacity is achieved by resorting to compatible and sustainable interventions. Through life management of structure is ensured by structural health monitoring. Proactive conservation strategy shall be implemented. It means preventive measures and intervention designed to avoid and minimize future deterioration or loss by acting before damage becomes visible. By investing in proactive maintenance and conservation practices, we can safeguard the structural integrity and resilience of modern heritage buildings, ensuring their continued relevance and viability for future generations. Starting from available prescription and recommendations, we have seen that the structural assessment of reinforced concrete built heritage requires an accurate process. It is aimed to benefit of unaccounted behaviors upon structural resistance, realistic loading conditions, and on actual service life. Codifying the process to enact the setting out of a recovery project for modern heritage reinforced concrete constructions will contribute to conserve, restore, and protect this important cultural asset. By considering scientifically sound strategies, retrofitting interventions can be often minimized, leading to manage the modern built heritage in a respectful and environmentally friendly way.